Hi, and welcome to section 7, where we are going to learn a new way to solve systems of equations. If you remember, we have solved systems of equations algebraically by using graphing, by using substitution, and by using elimination. Those are the 3 ways that we have learned before. We also talked about using a table, so I guess we talked about 4 ways. Today we're going to learn about something called Cramer's Rule. Cramer's Rule is another way to solve a system of equations. And to do Cramer's Rule, we have to be able to evaluate determinants. We're going to talk about what those are and how to evaluate them. So we have some new vocabulary. A determinant is a square array of numbers or variables enclosed between 2 parallel lines. So a determinant will look something like this. And a matrix has the square brackets that look something like this. So if you see the 2 parallel lines, that means find the determinant. If you see the square brackets, it just means this is a matrix. And we can find determinants for 2 by 2 or 3 by 3 matrices. You can actually find them for any square matrix, but the only ones we're going to learn to do by hand are 2 by 2 and 3 by 3 matrices. The diagonal rule is the special way that we're going to find third-order determinants. And a coefficient matrix, which is something that we'll use when we use Cramer's rule, is a matrix that only contains the coefficients without the variables. But we're going to start by talking about determinants. A second-order determinant is the determinant of a 2 by 2 square matrix. So I can only find determinants of square matrices. So there are 2 ways you might see it written, either DET, which means determinant of the matrix like this, or you'll see these 2 parallel lines, and that will mean find the determinant. So this one is pretty easy to calculate. It's just the difference of the products of the diagonals. So if you look here, we take A times D, and we write that first, and then we subtract B times C. So if we look at this example here, notice the 2 parallel lines, so that means find the determinant of this matrix. The determinant is a single number. So I do 4 times 6, which is 24, minus 5 times negative 3, which is negative 15. 24 minus negative 15 gives me 39. So these are pretty straightforward. If I want to find this determinant, I would do the same thing. 6 times 0 minus 4 times negative 1, 0 plus 4. So the determinant here would be 4. This is an example for you to try, so you need to find the value of this determinant. All right, if you did your math right, you should have gotten negative 2. 3 times 0 minus 2 times 1. 0 minus 2, which gives you negative 2. All right, what we're going to do now is we're going to talk about how to find a determinant of a 3 by 3 matrix. This is obviously a little bit more complicated, so take a second to read through these steps. So the first step is to rewrite the first 2 columns outside to the right of your determinant. Then we're going to draw in diagonals. We're going to draw diagonals from the upper left down and from the upper right down. We're going to find the sum of the products of the elements in the diagonals, meaning we're going to multiply everything along the diagonals. And then I'm going to add those numbers together, which I'll show you in a second. And then we subtract the second sum from the first sum. So let's take a look at an example, because this is easier to understand, I think, when you see it worked out. Okay, so we're going to evaluate this determinant. Notice the parallel lines. I need to find this 3 by 3. So I'm going to take these first 2 columns and rewrite them over here to the right of my determinant. So notice that this column is here, this column is here. So I just rewrite those. And then we are going to find the product of the elements of the diagonals. So here we go. Here is my determinant with my first 2 columns rewritten. I'm going to start and I'm going to do diagonals from the top left down. So I'm going to do 3 times negative 1, which is negative 3, times negative 3, which equals 9. Then I'm going to do another diagonal. Negative 2 times 0 times 1, which is 0. and negative 1 times 2 times 2, which is negative 4. Now I'm going to do diagonals in the other direction. So 1 times negative 1 times negative 1 is positive 1. Here I will multiply to 0, 2 times 0 times 3. Negative 3 times 2 times negative 2 is 12. So here I have my first set of numbers and my second set of numbers. What I'm going to do now is I'm going to add these numbers together. So when I add 9 plus 0 plus negative 4, I get 5. And when I add 1 plus 0 plus 12, I get 13. So now what I'm going to do is I'm going to find the difference of these numbers. And I'm going to always do this first one minus the second one. So we're going to take 5 minus 13, and we get negative 8. So the value of this determinant is negative 8. Again, notice the order. That's super important. I always do the bottom sum minus the top sum, or the first sum minus the second sum. Okay, so now you guys are going to try one. Hopefully you took good notes so that you can work this one out on your own. Okay, when you do this one, you should get 79. Here's the work. If you want to check and see what you did, notice here are my downward diagonals. So I got 0, 6, and negative 10. When I add those, I get negative 4. So that's my first sum. Then I do my upward diagonals, and I get 0, negative 8, and negative 75. When I add those together, I get negative 83. So I do my first sum of negative 4 minus my second sum of negative 83, and I get positive 79. All right, one place that we can use determinants is the area of a triangle. Obviously, we're used to the area of a triangle formula. It's 1/2 times base times height. But the area of a triangle can also be found on the coordinate plane using determinants. So if they give me the coordinates of my vertices, I can arrange those coordinates into a determinant. So my first set of coordinates goes here. So notice here they have the ordered pair negative 4, 3. My second pair of coordinates goes here, CD, 3, 1. And my third ordered pair goes here, which in this case is negative 2, negative 2. And then because we can only take determinants of square matrices, we fill out our third column with 1s. And if I take the determinant of that and then multiply by 1/2, I will get the area of the triangle. Be super careful here. You cannot distribute the 1/2 here. You cannot do scalar multiplication because these determinant bars act like a grouping symbol or like parentheses in PEMDAS. So you have to find the determinant first and then multiply by 1/2. So here we have a surveying crew who plots 3 points on the map that are the vertices of a triangular area. We're going to use a determinant to find the area of the triangle with these 3 vertices. So we're going to arrange them in our area formula. So here are my 3 ordered pairs that were the vertices of my triangle. Fill in the rest with 1s. And we're going to do the process of finding the determinant for a 3 by 3, which is the diagonals method. So they rewrote the first 2 columns out here to the side. Then we're going to go ahead and do the diagonals method that we just did. And we will add those 2 sets of diagonal products, and we will subtract them. So here I wrote in the numbers, hopefully that's a little more clear. So when I multiply down this diagonal, I get 0. Here I get negative 3, and here I get 4. And over here, they're showing you that they're adding them all together to get 1. Then I do my upward diagonals and get negative 18, 0, and 2. Add those together to get negative 16. And now I'm going to subtract. I'm going to take the first sum of 1 minus the second sum of negative 16. And I get 17 times 1/2, which is 8.5. So the area of this triangle is 8.5 square miles. All right, give this one a shot. Okay, the answer to this one is B, 5 square units. We're going to move on now and talk about Cramer's Rule, which is one of the reasons that we're learning about determinants. Cramer's Rule, remember, is another way to solve a system of equations. So if you look here, I have a system of two equations in two variables. Here, x and y are my variables. A, B, M, and F, G, N represent constants, coefficients, okay? So my coefficient matrix, which they're calling C, comes from the coefficients of x and y. So notice A, B, F, and G. That's my coefficient matrix. I just arrange those into a matrix exactly like they are without the variables. To find the solution of this system, I take the determinant of this matrix, M, N, B, G. So notice the M and the N are the constants from here, so they replace the x column and the y column stays the same. And I do that divided by the determinant of the coefficient matrix. Then over here, to find y, I leave my x column the same, A and F, and I replace the y column with M and N. Find the determinant, divide by the determinant of the coefficient matrix, and that will give me my ordered pair. Let's look at an example because I think that will make it much more clear. So we're going to use Cramer's rule to solve this system. Okay, so this is my coefficient matrix. Now I need to make two other matrices. If we look back here at the rule, I need the matrix for x and the matrix for y. Our book doesn't do this, but sometimes I think it makes sense to call them dx and dy, and we will find those. So my x matrix, again, I'm going to take the constants 28 and 8, and I'm going to replace the x column with those. So instead of 5 and 3, I'm going to write 28 and 8, but I'm going to leave the other two coefficients the same, 4 and -2. Then I'm going to do the same thing for y, except this time I'm going to replace the y column. So the x column stays the same, 5 and 3. I replace the y coefficients with 28 and 8. And then I'm going to calculate the determinant of all three of these. So to find the determinant of dx, we'll do 28 times -2, which is -56, minus 8 times 4. And that is going to give us -88. And to find the determinant for y, we'll do 5 times 8, which is 40, minus 28 times 3, which is 84. 40 minus 84 is -44. Then we also need to find the coefficient matrix determinant. So 5 times -2 is -10. 4 times 3 is 12. That gives me -22. So now to find the solution, remember my solution is an ordered pair xy. To get that, I have to do dx over c. That's going to be my x coordinate, and my y coordinate is dy over c. So all I have to do is take -88 divided by -22. That'd be my x coordinate. And my y coordinate is going to be -44 over -22. When I simplify that, I will get 4, 2. So that is the ordered pair where these two lines would cross. Remember, this still represents two lines that are crossing in this case. So in this case, there is a solution. One solution, 4, 2 would be the point where they would cross. Remember, we can always check any system by plugging our x and y coordinate into the original equations. So if we plug into our first equation, we end up with 28 equals 28, which works. And if I plug 4 in for x and 2 in for y in my second equation, I also get 8 equals 8, which works. That shows that this ordered pair is a solution to the system. All right, I want you guys to pause and try this one. Okay, the answer here was 9, 3. And here is some of the work for that. Your coefficient determinant should have been -24. Your x determinant should have been -216. Your y determinant should have been -72. Then when you divide the x determinant by c, you get 9. And the y determinant by c, you get 3. Okay? You see on your notes, this also works for 3 by 3 matrices. We're not going to focus on that right now in this video. We'll probably do an example tomorrow in class. So I will see you then.